Okay, so in today's video, we're going to be talking about Poisson's equation, and this is section 8.6 in the book. Okay, so we want to solve the following kind of equation. So we've got a Laplacian of a function u equals q. This thing here is called Poisson's equation, and it would be called Laplace's equation if q were 0, but now we're really considering the case where q is not 0, so we are continuing our study of non-homogeneous problems, right? Because the q not being 0 makes us non-homogeneous. And we're also going to say that we have some boundary condition, u equals alpha on the boundary. So we're not giving this like super explicitly because the boundary could be any shape. It could be like a rectangle, a circle, something like that. So we're just saying that u has some prescribed value on the boundary of our region that we're studying. And again, that boundary condition is non-homogeneous. So let me write this. This is non-homogeneous, non-homogeneous, since q and alpha are both non-zero. So we're going to be thinking about some strategies to solve this anyway. So first, let's consider some other problems. So let's consider a very closely related problem where we have the same equation, the same Poisson's equation. Now we're talking about u1. But on the boundary, we're going to say that u1 equals 0. So this is one kind of thing that we could consider. So again, this means, I'm going to write a star here. That's not a mathematical symbol. I'm just saying that star means that this equation holds on the boundary. And so does this one. This equation just holds on the boundary. And let's consider another group of equations. So now let's consider a variant of Poisson's equation that's homogeneous, that is to say Laplace's equation. So we have a 0 here. And then we're considering the non-homogeneous boundary condition. Okay, so we have these two problems. I'm labeling 1 and 2. Actually, I think I want to label this guy 1, this guy 2, and this guy 3. And then we can observe that if we take the Laplacian of u1 plus u2, then of course the Laplacian as a big derivative kind of thing is linear. So we find this, and we said that the Laplacian of u1 was q, and the Laplacian of u2 was 0, so their sum is q. And then if we think about u1 plus u2 on the boundary, let me write a little asterisk here to note that we're just thinking about the boundary, then u1 we said was 0 on the boundary, and u2 was alpha on the boundary. So we see that u1 plus u2 on the boundary is alpha. So we find that u1 plus u2, if u1 satisfies problem 2, like capital Roman 2, and u2 satisfies 3, then u1 plus u2 satisfies 1, right? So the point is that if we can solve 2 and 3, then we can put them together, just take the sum, and we'll be able to solve 1. Okay, so we've now decomposed our problem number 1 into two problems, 2 and 3, that we can then try to solve separately. Okay, so for 1, I'm going to think about 1 for a second. For 2, I should say, the first sub-problem. There are 2 strategies, and these strategies do work in different geometries, but we're going to assume let me say a few more comments about the different strategies, but we're going to, before I do that, we're going to just say that we're assuming that we have a 2D rectangle, and that's what we're working over. So here we have x equals 0, so x is going from 0 to L, and y is going from 0 to h as usual. And so we're going to see two strategies because basically there are two dimensions, but if there were more dimensions, we would see kind of more strategies, if that makes sense. But we're really just going to think about these two for the rectangle. So I'm going to call the first one strategy A. And all of these strategies really consist in taking a solution to the associated homogeneous problem, and then doing some magic to get it to work for the non-homogeneous problem. So we're going to take the eigenfunctions in this first strategy for the x part. So again, we're trying to solve, let me move this. We're trying to solve this problem 2 here. So we're going to take the eigenfunctions for the x part of this associated homogeneous problem, and we're going to assume then that u is equal to, so let me say something here before I read out this equation. So if if u were totally homogeneous, then and if it were really just like the x part, then we would know that the solutions were of this form, right? That's what we've studied. But now u1 is a function both of x and y, and we're saying that what's going to work here is where we don't consider just constant coefficients, but coefficients that are actually functions in y. This gives us the extra bit of wiggle room to account for the non-homogeneity. And I also want to say that, of course, there's a very nice symmetry here, where we could instead take the eigenfunctions for the y part, and then we could assume that u1 was some function bi of x, and then sine I pi y of L. And maybe I should have said, I didn't say this explicitly, that these guys here, as we know, are, of course, the eigenfunctions of the x part of this equation. Okay, so you could switch x and y is my point, because there's nothing in this problem distinguishing x and y. Okay, so to find now bi of y, this is our task, and we're of course going to use very similar strategies to what we use when it's just a constant. But first we're going to substitute into Poisson's equation. So we want to use the original equation up here, that the Laplacian of u1 is q. So we're going to substitute this kind of guess, you might call it at this point, for u1 into the equation that we know holds for u1. So that is that q is equal to the Laplacian of u1. And now let's substitute in our guess for u1. So we've got this guy. And now we'll see at the end of the lecture that there's a bit of trickiness with putting this guy into the sum, right? If the sum were finite, we would always, like with any kind of differential operator, we could put it into the sum, right? Because those guys are always linear. But there's a little bit of weirdness with a infinite sum. Here it's fine, but in the end of this lecture, it won't be fine. So just keep that in mind. And in this class, we're really not understanding theoretically like when it is and is not fine. But just be aware of this. That is making a difference here. in two parts of this lecture. So here we can put it inside, so I'll stop blabbering on about that. And if we put it inside, then what we're going to find is, so first of all, we're taking the double derivative with respect to x. So if we do that, the only x thing we have here is the sign, so a negative sign is going to pop out. Then we're going to get this coefficient thing here that's going to pop out twice. Nothing is going to happen to bi of y because it's just a function of y, not of x. And of course, if we differentiate the sign twice, well, we've already accounted for the minus sign and the coefficients coming out, and it will become a cosine and then back to a sine, so it's still a sine. And then we're going to add on the double derivative of y. And so this one, I mean, we don't know anything about bi, of course, we're trying to figure out what it is. So we're just going to write this. And we still have the sign here. Okay, and now you notice that we have in both parts here of this sum, we have this sign appearing twice, so we can factor that guy out. And what we find, I'm going to write it this way because we have a minus sign in front of the first one. So we can write it like this. And now we can use how we know to extract coefficients to extract the coefficients here. So what we find is that this coefficient here, I mean, it is a function of y, but if we think maybe about every single y as kind of just being like one point and not thinking about it as a function, but just as a series, a whole bunch of coefficients, one for every y, then we can just use what we normally do to extract this. So we find that this coefficient here is, oops, let me put parentheses around that guy, is the integral of q times sine I pi x over L dx dy. And of course, we're taking this integral from 0 to L in the x direction and 0 to h in the y direction. I'm just not writing it down because it would, in my opinion, get a little bit messy. And then we have the eigenfunction squared here at the bottom. So this is the normal integral thing that we always do. And we can actually evaluate the integral in the denominator. We do that all the time. And we know that it's 2 over L. And the numerator, of course, we cannot evaluate because we have no idea what q is. It could be anything. So now we find this equation. Let me just write it down. Let me write an arrow here. So we have this. And now this gives us the following equation. Okay, so we have this ODE where the unknown is BI, and we also have that BI of 0 is 0, and BI of H is 0, because if we go back up to our problem that we're trying to solve, this guy too, we remember that the boundary conditions are 0 everywhere. Okay, so we have this problem now. This is a second order ODE, linear ODE, with these boundary conditions. So this is solvable, but if you think back to what you know about ODEs, this is actually pretty weird and difficult. Not because of the equation itself, the differential equation itself, but because of the boundary conditions. So normally when you have, say, a second order ordinary differential equation, then you are going to hope that you have two initial conditions, one specifying the initial value of BI and the other one specifying the initial derivative of BI. And here we do have like two conditions, but they're not initial. They're not of this form that we have like bi of 0 equals something and bi prime of 0 equals something. We have something different, which is that we have two values of bi at different places. So I want to make the point that this, I don't think you will have learned how to solve these kinds of equations really, and maybe more importantly, so an ODE with these kind of two initial conditions, that always has a solution, a unique solution. But these kinds of problems where we don't have two initial conditions, but two boundary conditions, they don't always have solutions, and maybe also not unique solutions. So this is kind of tricky as an ODE. So I want to just write this down. So this is difficult as it is an ODE boundary value problem. It's an ODE plus some two boundary conditions and not an initial condition problem. Okay, so I just want to remark that there's something weird going on here. It's a bit difficult. We're not going to learn how to solve these kinds of ODEs with boundary values in general. I mean, we of course have seen this a little bit over and over again through the course, but not in a general theory. The solutions for this particular guy are described somewhere in the book, I think chapter 9, but we're not going to go over that in this class. So we're just going to quote the solutions, relying on the fact that other people have figured this out. So the solutions to this particular ODE plus boundary values are of this form. And this is going to be a little bit crazy. So we have sinh of I pi h minus y over L. And then here we have the integral from 0 to y of 2 over L, integral 0 to h, 0 to L, q of z, sine I pi x over L, dx dy. So when I say q over z, we're substituting in z wherever y appears in q. And here we have sinh I pi z over L dz. Okay, and then we have plus something very similar, I pi y, sinh of I pi y over L. Now we're taking the integral from y to h of this other guy, 2 over L, 0 to h, 0 to L, again q of z, sine I pi x over L, dx dy, sinh I pi h minus z over L, dz. Maybe I should write this guy here. Okay, so these are the solutions. It's kind of awful, but thankfully there are some other strategies that I think are a bit nicer to use. Okay, so let's look at those. The second one I'm going to call strategy B. And for this one, we're going to take the eigenfunctions not of the Laplacian of u equals 0, but of the Laplacian of u plus, and we call this u1 plus lambda u1 equals 0. So we have this extra lambda u1, and we're going to assume, very similarly to how we did it before, that u1 is equal to now some constant times, or some linear combination of sine I pi x over sine, I want this to be a j pi x over L. Okay, and just to be clear, as we've seen many, many times, these guys here are the eigenfunctions. Right, and so in particular, I mean this guy itself as a whole, or each one of these guys for each I and j, is an eigenfunction for this equation. We can say it's a two-dimensional eigenfunction because I have some typos here, excuse me. So this should of course be y, and then on the bottom it should be h. So sorry, so these eigenfunctions, we can call them two-dimensional eigenfunctions because each one has an x part and a y part, right? So they're both functions that take values in x and y. Okay, so now we want to find bij, and remember that's a constant, right? Because we already have, I mean, in some sense, we already have the dependency on x and on y, right? So it makes sense that this guy doesn't introduce then the dependency on, as it did in the last strategy, the dependence on y. We're just now looking for some constants. Okay, so how we do that is we again substitute into the equation that we're trying to solve. So we again, our equation is q equals the Laplacian of u1. And now we assumed that u1 is this guy. But of course, we're going to take the Laplacian of this guy. And again, here we can, it's totally fine, we can move the Laplacian into the sum. So I'm going to do that now. So we still have the same kind of sum. And let me just pull bij out and now take the Laplacian of these two signs. So the first thing we do is take the double derivative with respect to x. So just like before, basically, we find this. And then we also take the Laplacian with respect to y. And since, of course, these two, this thing is pretty symmetric, j. It's pretty symmetric with respect to x and y. It's going to look exactly the same, or basically the same. Okay, so we have this. And now you notice that these terms here are the same in both of these guys, so we can factor that out. So now, and we can also factor out the negative. So let's write I pi over L squared plus J pi over H squared times now these sign terms. And then we can notice that this guy here is the eigenvalue corresponding to this eigenfunction. So let's, let's replace that to make it a little bit more comprehensible. So we can replace it with lambda ij sine I pi x over L sine j pi x over h. So I want to say that, let me mark this equal sign with an asterisk and say that this fact that this guy here is the eigenvalue. If it's kind of buried in your memory, it's in section 7.3 and in the corresponding lecture. Oh, right, I'm done here. Okay, so now we have Q equals this crazy sum. We want to figure out what this coefficient is here. And we find then, using the same integral strategy that we always have, that Bij is, or let me actually just write the whole coefficient. Make a bit more sense. So we have this whole coefficient here is equal to the integral of Q times our eigenfunction for that I and j over the integral of the square of that eigenfunction. Okay, and now we have, well, we almost have a formula for Bij. So of course then Bij is just -1 over this eigenvalue times this big integral thing. Okay, so the next thing that we're going to do, so we've now finished strategy B, and we're going to see actually that we can use it not just to, let me go up here, where is it? Right, not just to solve this guy 2, but actually to solve 1, and we're also going to think about it in any geometry. So we thought about both strategy A and strategy B as being on a rectangle, so we're thinking about very particular shape. But now we're going to think about using strategy B not only when we have a completely non-homogeneous equation, but also in any geometry. So we can use strategy B on U, that's the variable in the first problem, not just UI, that was a variable in the second problem, and also in any geometry. So we're going to let phi I be the eigenfunctions of the Laplacian of u plus lambda u equals 0. We're giving them a very abstract name because since the geometry could be anything weird, then the eigenfunctions could look very different in different geometries. So we're going to, as before, assume that u is some linear combination of all of these phi i's. And now I'm going to point out that we cannot, if we do the same kind of calculation that we did in the first two strategies, we cannot push the Laplacian inside of the sum. So we cannot say that the Laplacian of u is equal to the Laplacian of the big sum of bi times the Laplacian of each of the phi i's. Since u and phi I, this is one of the things that needs to be satisfied for this to be possible. They satisfy different boundary conditions, because the phi I are the eigenfunctions of this equation. Maybe I can be a bit more explicit here, with homogeneous boundary conditions, and the u itself doesn't have homogeneous boundary conditions. Okay, so instead we do the following calculation. So we have that each bi is, so we're kind of doing this integral thing first. So we're kind of switching the order just to kind of cleverly get around this problem. So we're going to first write down the integral. So looking at the equation here of u, we see that each bi is equal to this quotient of integrals. And again, I am writing two integration signs and dA as if we're looking over a two-dimensional solid. But you can also do this over a volume, right? So then it'll be maybe 3 integral signs, dv, or really any shape. So I have to write something, so I'm just thinking about it as a surface. Okay, so we have this, and then I'm going to say that this is equal to something else, and we're going to use the fact that phi I is negative Laplacian of phi I over lambda I, right? And that's because it is a solution to this equation here. So I'm going to now substitute phi I in the numerator for this guy. So we're going to see a negative sign, u Laplacian of phi I, and then the that lambda I in the denominator pops out because it's just a constant, right? So we have lambda I times the same integral. And now we're going to use Green's formula, which hopefully you learned about, but we're just taking it as a black box, really. It's not so important to understand. So by Green's formula, we see that the numerator the numerator here is equal to this expression. This n hat, as always, is the normal vector to the boundary at each point. And this this kind of thing here, this kind of integral, hopefully you're familiar with it. I think we've also seen it very briefly, though, in this class, is the, well, so if we're looking at two-dimensional solid, then it's the line integral around the boundary. And if we're looking at a volume, then it's the surface integral around the surface. Oops. Okay, and then the right thing. The denominator is going to be exactly the same. We haven't done anything with that. And now we can evaluate a little bit what's going on in the numerator here. Again, we're not changing the denominator. So we have phi I. Our original equation for u said that the Laplacian of u is equal to q. So here we're just going to substitute the Laplacian of u for q. And then here we know that phi I, here, so we're taking this integral over the boundary. And so this is not the case for u, but phi I satisfies homogeneous boundary conditions, so it's always 0 on the boundary. So this term, since phi I is 0 on the boundary, and we're just doing this integral on the boundary, goes away. And our boundary condition for u says that u is alpha on the boundary, so we're going to substitute u for alpha. So we got the Laplacian here of phi I dotted with n hat ds, that second term of course has disappeared, and now we have the same thing on the denominator. And let me write here, so just to be clear. So we have, since the Laplacian of u is q, that's our equation for u. U equals alpha on the boundary, that's the second equation for u, and phi I equals 0 on the boundary. Okay, so now we have this expression for bi, so in principle we can completely solve u using, like, if we already know how to find the eigenfunctions of this situation, and then using this formula for bi. And so let's just wrap this up with a little bit of a sanity check. So if alpha equals 0, so our original equation, let me write down the original equation. So we had this, and u equals alpha on the boundary. Again, the asterisk just means that this equation holds on the boundary. So this was 1, and 2 was the same, but with homogeneous boundary conditions. So we want to just make a bit of a sanity check here to check that these different strategies do coincide. So the second strategy, or this last strategy that we've seen, it applies in the first case, but in particular it would apply also if alpha were to equal 0. So if alpha equals 0, we just want to check that what we just got, should coincide with what we found above. And if we remember what we found above, both are the following. So we find for both of them that bi, so here if we plug in alpha equals 0, of course this guy is going to disappear. So we find this integral here for bi when alpha equals 0, according to the most recent strategy that we had. And if we looked at what we did above, particularly for the case that alpha equals 0 here, we do find the same thing, right? So this here is the phi I, and here we have the phi I squared, here we have q, and here we have -1 over the eigenvalue, and that's the same as what we found in the very last strategy. Okay, so that's it for the lecture. Now there are 2 exercises that I want you guys to do. The first one's just one exercise. So for the first one, we're going to consider some uxy on a rectangle. So as usual, x is going from 0 to L, y is going from 0 to h. And we want to solve the following problem. So the Laplacian of u equals q. And then we have these boundary conditions on each of the sides. So at x equals 0, we have 0. At x equals L, we have 1. At y equals 0, we have 0. And at y equals h, we have 0. So we have 0 on all sides except for x equals L. And we want to use strategy B for, of course, alpha not equal to 0 because it doesn't equal 0 here. So we're just going to use this most recent thing here that we did in the lecture for this problem. And the second one is exercise 8.6. I think something like 3. I haven't unfortunately written it down. So we're going to, but it does come from the book. So we want to consider u. Now the variables in u are r and theta on a disk of radius a. And we want to solve this equation that the Laplacian of u equals q, and that on the boundary of this disk we have 0, so we have a homogeneous boundary condition. Okay, so that's it. The solutions for these exercises will be on Canvas as normal. I really encourage you though to do them, try to do as much as possible before looking at the solutions. That's how you'll learn the most. Right, so that's it. There will be homework on this due on Thursday. Make sure to do that. And if you have any questions, please ask them on Piazza. I think that would be the best place. Okay, see you on Thursday.